Alright, this is Malachi, and we are going to work on 11.1, and this is the homework intro video, help video, whatever. Alright, so our first problem, 11.1.1, is a fairly straightforward problem that just has you compute a cross product. So we want to cross m, which is given by 6, 2, negative 1, with n, which is 2, negative 1, negative 3. That's a negative sign, right? So by definition of the cross product, we just expand this out into matrix determinant ijk on this first row, and then we're wanting to do m crossed with n. So the order is very important when we do this. We want to put m first right here, m, and we want to put n here. All right. So when we write this out, we have 6, 2, and negative 1. And n is 2, negative 1, and negative 3. So now what we need to do is the cofactor expansion to find this determinant. So basically what we do is we blot out this row, this column, expand it into I times the submatrix, or the determinant of the submatrix of this submatrix, right? And we continue to do this for I, j, and k, and also may I remind you that we have this checkerboard pattern of plus, minus, and plus when we do this determinant expansion, okay? All right. So let's see if we can clear this and then move on to 11.1.2. And, oop, oh, too much. Okay, so now we move on to 11.1.2. This is also a fairly straightforward problem that just relies on the definition of a cross product. So I'm going to give you this equation, which is absolutely imperative for this problem. The magnitude of the vector A cross B, because A cross B is a vector, is equal to the magnitude of A times the magnitude of B times sine of the angle between them. Okay? So in this problem, we're given two vectors. We're given the length, or the magnitude, as well as theta, okay, and we're given this for the two vectors. So what we want to do is we want to find the angle called psi, which is equal to theta minus alpha, where theta is one of the angles and alpha the other angle. And we also want to take the lengths, and we basically just use this definition to compute it. So that's part A right there. Now if I go back, erase this with this now. Okay, then part B is also just as straightforward. The best way to do it is basically when we have two vectors, they're added together. So we have like a vector A here, we have a vector B here. When we add this vector together, we get the vector A plus B right here. In fact, let me color code this a bit. This vector A plus B here, you can think of it like we have this parallelogram right here, side lengths A and B. So the easiest way to do this is to just convert the two vectors they give you into I and J format, and then just add them. So stack and rack, right? So now if we move on to 11.1.3, okay, just get rid of this here. Okay. Now 11.1.3. This kind of problem is a relatively quick problem. We just use the definition torque is equal to R crossed with F, And then remember that the magnitude of a cross product is again equal to the magnitudes of the vectors times sine of the angle between them. Let's see if I can find the calculator here. And just as a quick warning, the correct answer is 0.3434303 Newton meters. Okay. An incorrect answer, which is probably the most common one, would be an incorrect answer is 0.0855. So I'm just, obviously these are not the same thing, they do not equal each other, but just as a fair warning, pay attention to your angle. Let's see if I can figure out how this works. Ah, there we go, it's back. Okay. Now if I erase, I need to invest in like a bigger screen, or maybe a smaller brush size. Okay. Alright, and now we have 11.1.4. This problem involves a bit of theory. So what I'm going to do is I'm just going to say there is one identity that is absolutely imperative that you use on this problem. It's basically that when you do a cross product, by definition, you are, so here if I draw a 3D diagram, this may be a bit more helpful. So if you have a vector A, it's crossed with a vector B, then the vector product A crossed with B will spawn this vector that is orthogonal or perpendicular to both of the vectors. So the quickest way to verify that is through the dot product. No. Dot product. And you'll come up with the very true statement, -5 is not 0. Alright, so let's keep moving. Next problem. See the light at the end of the tunnel, and we're almost done. Okay, 11.1.5. This also requires, just again, direct computation, because torque is equal to R crossed with F. We're given R and we're given F. So it's just real simple. You set up in this matrix, determinant ijk, the R components that stretch out in ij and k, and then the F components that stretch out here. So it's nothing that you haven't seen before. The one caveat with this problem though is that on part B, when you change your R from 0.6, your force doesn't change, but your R does change. So R changes. And so you'll expect a different answer, and they are different. So I believe that when you compute this one, you'll get -7 K Newton meters, and this one will be 11. Okay, but that's neither here nor there. So let's go ahead and move on to the next problem. Alright, in this problem, probably be helpful if I make a decent diagram of it. So we're given an equilateral triangle here. So all the side lengths are the same here. And then we're also given that there's a vector F1 here, a vector F3 here, and a vector F2 right here. And okay, so it says two forces F1 and F2. So F1 and F2 on two sides of an equilateral triangle. So it's right here and here. I just realized my color coding is a bit off. That's F1 is this blue arrow right here. So that's F1, F2, that's F3. Okay. Says find a third force F3 to be applied at this point B right here, such that there'll be the total torque is 0 about this center point here. So the fastest way of doing this is, again, using the definition of torque. Torque is equal to R crossed with F. And so in a way, you can kind of do a two-dimensional sum of the F's, and if they can cancel out, then you have no force, i.e. if the sum of forces is equal to 0, then something crossed with 0, something crossed with 0, the 0 vector is also 0. So that's a very powerful tool on this kind of geometric problem. Alright, now I'll leave you there.